Lesson 3. Using Electromagnetic Waves. Reading Guide. Key Concepts. Essential Questions. How are different types of electromagnetic waves used for communication? What are some everyday applications of electromagnetic waves? What are some medical uses of electromagnetic waves? Vocabulary. Broadcasting. Carrier wave. Amplitude modulation. Frequency modulation. Global positioning system. How do you use electromagnetic waves? There are few things you do that don't involve some type of electromagnetic wave. Think about a typical day. Perhaps a clock radio wakes you in the morning with your favorite music. You are warm under your blanket because infrared radiation from your body changed into thermal energy. When you finally crawl out of bed, you turn on a lamp and use light to see which clothes to wear. These are just a few of the ways you use electromagnetic waves. In this lesson, you will read about common uses for all types of electromagnetic waves. Radio waves. It probably is no surprise to you that radio and television stations use radio waves to send out signals. Radio waves can pass through many buildings, yet they don't carry enough energy to harm humans. The wavelengths of radio waves are long enough to go around many obstacles. They travel through air at the same speed as all electromagnetic waves. In the past, it might have taken minutes, hours, or even days for news to travel from one part of the United States to another. Today, you can watch and listen to events around the world as they happen. Broadcasting is the use of electromagnetic waves to send information in all directions. Broadcasting became possible when scientists learned to use radio waves. Radio and television. How do your radio and television receive information to produce sounds or images? A radio or TV station uses radio waves to carry information. Each radio and TV station sends out radio waves at a certain frequency. The station converts sounds or images into an electric signal. Then the station produces a carrier wave, an electromagnetic wave that a radio or television station uses to carry its sound or image signals. The station modulates or varies the carrier wave to match the electric signal. The signal then gets converted back into images or sounds when it reaches your radio or television. Two ways a station might change its carrier wave are shown in Figure 8. Amplitude modulation, AM, is a change in the amplitude of a carrier wave. Recall that amplitude is the maximum distance a wave varies from its rest position. Frequency modulation, FM, is a change in the frequency of a carrier wave. Changes in frequency match changes in sounds or images. Key concept check. How are radio waves used for communication? Digital signals. Television stations and some radio stations broadcast digital signals. To understand types of signals, look at the amplitude modulated wave in Figure 8. Notice how the wave changes smoothly from high to low. This type of change is called analog. A digital signal, however, changes in steps. Stations can produce a digital signal by changing different properties of a carrier wave. For example, the station might send the signal as pulses or a pattern of starting and stopping. The wave might have a code of high and low amplitudes. Sounds and images sent by digital signals are usually clearer than analog signals. Transmission and reception. The way a radio station broadcasts a signal is shown in Figure 9. A transmitter produces and sends out radio waves. An antenna receives the waves and changes them back to sound. Television transmission is similar, but for cable television, the waves travel through cables designed to carry radio waves. The wavelength of an AM carrier wave is typically a lot longer than the wavelength of an FM carrier wave. This means AM signals can pass around obstacles and travel farther than FM waves. AM waves also are long enough to reach Earth's upper atmosphere without scattering. FM waves typically have higher frequencies and more energy than AM waves. Therefore, FM waves usually produce better sound quality than AM waves. Microwaves. You've probably used a microwave oven to heat food. Did you know you also use microwaves when you watch a television show that uses satellite transmission? Like radio waves, microwaves are useful for sending and receiving signals. However, microwaves can carry more information than radio waves because their wavelength is shorter. Microwaves also easily pass through smoke, light rain, snow, and clouds. Cell phones. A cell phone company sets up small regions of service called cells. Each cell has a base station with antennae, as shown in Figure 10. When you make a call, your phone sends and receives signals to and from the cell tower. Electric circuits in the base station direct your signal to other towers. A signal passes from cell to cell until it reaches the phone of the person you called. Number 1. Monitor stations relay microwave signals from satellites to the master control station. Number 2. The master control station tracks each satellite's position and condition. Number 4. Each GPS satellite constantly broadcasts a signal about its position and the time the signal is sent. Number 5. A GPS receiver detects signals from nearby satellites. It compares the time a signal was sent to the time it is received to determine its distance from each satellite. Number 3. Ground antennae transfer signals from the master control station to satellites. These signals might correct a satellite's clock or position. Communication satellites. Have you seen a sports event or heard a news story from around the world on your TV? Information about the sounds and the images probably traveled by microwaves from a satellite to your TV. Some homes have a satellite dish that receives signals directly from satellites. Satellites send and receive signals similar to the way antennae on Earth do. A transmitter sends microwave signals to the satellite. The satellite can pass the signal to other satellites or send it to another place on Earth. You can use satellite signals to find directions. The Global Positioning System, GPS, is a worldwide navigation system that uses satellite signals to determine a receiver's location. As shown in Figure 11, at least 24 GPS satellites continually orbit Earth, sending out signals about their orbits and the time. Receivers analyze this information to calculate their location. Key concept check. How are microwaves used for communication? Infrared waves. You read in Lesson 2 that vibrating molecules in any matter emit infrared waves. The wavelength of the infrared waves depends on the object's temperature. Hotter objects emit infrared waves with a greater frequency and shorter wavelength than do cooler objects. Scientists have developed technology that produces images showing how much thermal energy a person or thing emits. Infrared imaging. Thermal cameras take pictures by detecting infrared waves rather than light waves. They convert invisible infrared waves or different temperatures to different colors so that your eyes can interpret the information. Medical professionals use thermal imaging to locate areas of poor circulation in the body. Thermal imaging of a building can identify areas where excessive thermal energy loss occurs. Can you see in the dark? Night vision goggles, such as those in Figure 12, use infrared waves similar to the way a normal camera uses light. Using the small amount of infrared light present, the goggles produce enough light that objects can be seen easily in the dark. Imaging Earth. Scientists launch satellites that detect and photograph infrared waves coming from Earth. These infrared images might show variations in vegetation or snowfall. Some images can even show a fire smoldering in a forest before it bursts into flame. The thermal image in Figure 13 shows the lava flow from a volcano. Reading check. What are some ways in which infrared images help humans? Light. The sun provides most of Earth's light, but light emitted on Earth also has important uses. Think about how difficult driving in a city would be without automobile headlights, streetlights, and traffic signals, such as the one in Figure 14. Without electric lights, homes and businesses would be dark at night. Televisions, computers, and movie theaters also rely on light. Some forms of communication rely on light that travels through optical fibers, thin strands of glass or plastic that transmit a beam of light over long distances. Ultraviolet waves. Too much exposure to ultraviolet waves can damage your skin, but these same waves also can be useful. Certain materials glow when ultraviolet waves strike them. The materials absorb the energy of the waves and re-emit it as light. Credit cards, for example, have invisible symbols stamped on them using this material. If a store clerk holds the card under an ultraviolet lamp, the symbol appears. Scientists also can identify some minerals in rocks by the way they glow under an ultraviolet lamp. Ultraviolet waves also are useful for killing germs. Just as your skin can be damaged by absorbing the energy of ultraviolet waves, germs also can be damaged. Food manufacturers might use ultraviolet lamps to kill germs in some foods. Campers might use ultraviolet lamps to purify lake water. Key concept check. What are some everyday applications of electromagnetic waves? Medical uses. In hospitals and clinics, having a germ-free environment might be the difference between life and death. Medical facilities sometimes clean tools and surfaces by bringing them near an ultraviolet lamp. Some air and water purifiers use ultraviolet light to kill germs and reduce the spread of disease. Ultraviolet light has other medical uses. For example, exposure to ultraviolet waves can help control or cure certain skin problems, such as psoriasis. Several times a week, the patient's skin is exposed to ultraviolet light. The waves carry enough energy to slow the growth of the diseased skin cells. Another use of ultraviolet waves is shown in Figure 15. The dentist is using ultraviolet light to harden an adhesive in just a few seconds. Without ultraviolet light, adhesives might take several minutes to harden. Fluorescent light bulbs. Light bulbs like the one shown in Figure 16 use the energy from ultraviolet waves to produce light. Similar to the way a symbol on a credit card glows under ultraviolet light, certain chemicals inside the light bulb glow when they are exposed to ultraviolet light. When you flip a switch to provide electricity to the bulb, an electric current flows through a gas inside the bulb. The heated gas emits ultraviolet light. This light strikes a chemical that coats the inside of the bulb. The chemical absorbs the energy of the ultraviolet waves and re-emits it as light. Reading check. How does a fluorescent light bulb use ultraviolet waves? X-rays. Ultraviolet waves can be dangerous because they can pass through the upper layer of your skin. X-rays have even more energy than ultraviolet waves and can pass through skin and muscle. Although this property makes X-rays dangerous, it also makes them useful. Two important uses of X-rays are security and medical imaging. Detection and security. Have you ever had your luggage scanned at an airport, as shown in Figure 17? X-rays are useful for security scanning because they can pass through many materials, but metal objects block them. Computers can form images of the contents of luggage by measuring how different materials transmit the X-rays. Medical detection. You might have had an X-ray taken by a dentist or a doctor, similar to that shown in Figure 18. X-rays pass through soft parts of your body, but bone stops them. When X-rays strike photographic film, the film turns dark. Light parts of the film show where bone absorbed the X-rays. A doctor can obtain even more detailed images using a computed tomography (CT) scanner. The scanner is an X-ray machine that rotates around a patient, producing a three-dimensional view of the body. Reading check. How are a CT scan and a normal X-ray different? Gamma rays. Because of their extremely high energy, gamma rays can be used to destroy diseased tissue in a patient. Gamma rays also can be used to diagnose medical conditions. Recall that gamma rays are produced when an atom's nucleus breaks apart or changes. In a procedure called a positron emission tomography (PET) scan, a detector monitors the breakdown of a chemical injected into a patient. The chemical is chosen because it is attracted to diseased parts of the body. The detector can find the location of the disease by detecting the gamma rays emitted by the chemical. Key concept check. What are some medical uses of electromagnetic waves?